Okay, so good morning, everybody. Today we are going to start the chapter 3 and to finish, in fact, the chapter 3 of the course, okay, that deal with two technical results, namely the Girsanov theorem and the martingale representation theorem. Okay, so I will in. So why we are going to do this, okay, before to start the financial part of the course. Because these two technical results will be the one that will ensure two nice properties of the Black-Scholes model. In financial model in general, okay, we want to obtain model that fulfill the absence of arbitrage opportunities. So in good models, good financial models, we don't want arbitrage opportunities. Arbitrage opportunities are just financial strategy allowing to win money without taking risk. We don't want such strategies in general, okay, in good financial markets, okay? And it will be related to the first result we are going to see today, that is the Girsanov theorem. Secondly, in a good market, we want to be able to price, okay, a lot of derivatives. And in order to be able to price, okay, in a perfect situation, it's a situation where I am able to price everybody, okay, that is called the case of complete markets, okay? And in the Black-Scholes model, to prove that this market is complete, okay, we are going to use the martingale representation theorem. And what is the meaning of the theorem is just to say that if I am interested in square integrable martingale with respect to the Brownian filtration, necessarily they are stochastic integrals, okay, of an element in L2 prog. So it means that I know in the case of the Brownian filtration, what is the form of every square integrable martingale. So something that is really strong, a really nice result, okay, that is called the martingale representation theorem. And in the financial setting, okay, you will see that we are going to use this result in order to prove that, in fact, I am able to hedge any contingent claim. Okay, so that is any financial derivatives, okay, of the European type. Okay, so let's start first with the Girsanov theorem. And in fact, I have already done, I have beginning the job, in fact, concerning this point. So let me remind, excuse me, what we have done. Sorry for this. So in this whole chapter, okay, dt will be a standard Brownian motion defined on my probability space omega AP. Omega is a set, A is sigma algebra, P, what I call the probability, the historical probability that it will be in the financial setting. Okay, and I denote classically by FTB the filtration related to the Brownian motion. And in what follows, okay, I will denote by E. It's something that is important because here we are going to deal with several probabilities, okay? So with several possible expectations, okay? And I give a name to the expectation under P that is just E, okay? So, so let me just connect my pad, okay? It doesn't connect, so excuse me, some technical little problem. Cheat, I have the pad, yes. Okay, so in fact, here, implicitly, when I will denote expectation of X, it will be the expectation under the initial probability P. Okay, the one that is related to my Brownian motion. Okay, So when I define a Brownian motion, of course, the definition of my Brownian motion depends on P, because, okay, I impose, for example, the fact Vt minus Bs follows the N0 T minus S. It follows the N0 T minus S, okay, with respect to the probability P. Okay, so I have this here. It's the integral with respect to omega of x of W dP of W. Okay, so this notation concerning expectation will be, okay, the one with respect to my initial probability P. Okay, so let me remind a result we have seen together, okay, at the end of the chapter 0. At the end of the chapter 0, I have proposed a little exercise that was the following. I start with a Gaussian random variable under P with a mean M and a variance sigma square, okay? And the idea of this exercise was to find a probability Q equivalent to P that make this random variable centered, okay? So the aim here was to change the probability to pass from P to Q in order to pass from X following the NM sigma square to X following N0 sigma square. And we have obtained explicitly what is Q. In other words, what is the density of Q with respect to P. And we have proved that if I take this density for Q with respect to P, I obtain for X, okay, N0 sigma square under Q. Okay? So I make something that is Gaussian, but centered, okay, changing the probability. And in fact, the aim of the first part of this video will be to do the same if I replace X by a shifted Brownian motion. And we are going to enter the details in the next slide, but the idea is in some sense, okay, to propose a dynamical extension of this result if I replace X by a particular Gaussian stochastic process, and changing the probability, I want to make this particular Gaussian process a Brownian motion. Okay? So it's exactly what we are going to do. Okay. The process we are going to be interested in is the following one. I consider Bt tilde, okay, that is just my initial Brownian motion plus M time t. M being a fixed real number, okay? So I have what I called, okay, a shifted Brownian motion, okay? In some sense, I translate it, okay, by this coefficient that is time dependent, okay? So I say the following. If I am under P, under the probability P, I know that Bt is a Brownian motion. Okay, Bt is a Brownian motion. And I define, so Bt tilde as Bt plus M time t, where my M will be fixed, okay, in the whole beginning of the chapter. And I say the following. In fact, in general, Bt tilde is not a Brownian motion. Bt tilde is a Brownian motion under P if and only if, but the only possible situation is the case where M is equal to 0. It's exactly what I have written here. Okay, so if I transform initially my Brownian motion B this way, I will obtain a new stochastic process that is a new Gaussian process, in fact, with independent increments and so on, but that is not in general a Brownian motion. The only case where is it a Brownian motion is the case where M is equal to 0. So how to prove this? It's very basic to prove this, okay? That is, of course, for this side, it's okay, because if m is equal to 0, I don't have this term, so bt tilde is equal to bt, and bt is a Brownian motion under p, so bt tilde will be a Brownian motion under p. So I have no problem with this one, okay? And now let's suppose that bt tilde is a Brownian motion under p, okay? And let's prove that m is equal necessary to 0, okay? So I have several ways to do this, but in particular, if bt tilde is a Brownian motion under p, so I do the implication from the left to the right. If bt is a Brownian motion under p, I know that bt tilde is a martingale under p. Okay, it's a result we have proved at the beginning of the chapter 1. Okay, that was that a Brownian motion, okay, is a martingale under the underlying probability. So in particular, if I compute the conditional expectation of bt tilde given given fsb for t strictly greater than s, okay? But if I am a Brownian motion, okay, I am a martingale, so I am equal to bs tilde, okay? So I have this, but what is this quantity here? But this quantity is equal by definition to bs plus ms. And what is this quantity? It's the conditional expectation of bt plus mt given fsb. And so this is equal to what? So mt is a number, so no problem. Okay, I can extract it from the conditional expectation, and I have the conditional expectation of bt given fsb, but I know that the Brownian motion, okay, is a martingale under p. So here I have simply bs using the martingale property of the Brownian motion b. And so I am in the situation where bs plus mt is equal to bs plus ms with t strictly greater than s. It implies that m is equal to 0. So I see from this little reasoning here that in order to make this one a Brownian motion under P, I don't have the choice. I need to take m equal to 0. That is the only situation where this kind of process is a Brownian motion, is if I come back to my initial Brownian motion B. Okay? And my objective here will be to find another probability Q equivalent to P, so equivalent to my initial probability, that make bt tilde a Brownian motion under Q. So I know that in general, bt tilde is not a Brownian motion under P. I want to change it in order to make bt tilde a Brownian motion under this new probability. Okay, so this is the aim here of the version we are going to see of the Girsanov theorem. Okay, and you will see that the version I will prove now, okay, will be exactly the version I need in the case of the Black-Scholes model. Okay, so this is what I want to do. And if you have understood what I have said, in fact, in some sense here, I want to make m equal to 0, changing my probability. And that's why there is a link with the previous result. Because in the previous result, you have something that allows you to transform a general Gaussian random variable into a centered one, that is into a Gaussian random variable with m equal to 0. Okay, so there is a link between the two things. Okay, so let's do the job. So I said the following. I have defined bt tilde as bt plus m times t. And so I know that under the probability P, I know that this one follows N0T because it's the Brownian motion BT under P, okay? And I add just a constant, so I know that this one follows a Gaussian with a mean equal to M times T and a variance equal to T, okay? So in fact, here I have a Gaussian random variable b tilde that is not centered because it has a mean equal to mt, okay? And the idea will be to use this result here in order to change the probability to make it centered. So using the exercise 0.6.1, okay, from the chapter 0, I can say the following, okay? If I defining defining, okay, let's say I write it qt because it will depend on t at this time, okay? Defining qt by d qt over dp equal to exponential minus, so what I have to do, in fact, so keep in mind what I have to do. So I have to use this result. I will apply this result, okay, with something that has a mean mt, a variance t, and with capital X that is equal to bt tilde. So I have to apply this formula here. So let's do. So it is what? Exponential minus m times t, that is the mean here, multiply by bt tilde, okay, divided by sigma square, that is equal to t in my situation, plus the square of the mean, that is m t square, over 2 sigma square being t. So defining qt by this expression, we know that under qt, bt tilde follows the n0 t. So if you want, concerning what I have said just previously, where my aim was to make m equal to 0, okay, in order to make bt tilde a Brownian motion under P, but here, a priori, I am not able to impose the choice of m, but changing my probability, okay, I will do something that is in some sense equivalent to consider m equal to 0. So under qt, I have this, okay? So let's have a look on this expression here. So you see first that I can simplify this one and this one. I can simplify the t with the t square here. So I obtain here, let's write it in two steps, okay, exponential minus m bt tilde plus m square t over 2. What is bt tilde? Bt tilde is equal to bt plus mt. So I can plug inside here to obtain exponential minus m bt plus mt plus m square t over 2. And I will have a little simplification because here I have exponential minus bt, no problem, okay? And then I have m square t over 2 minus m square t. So I obtain minus m squared t over 2. And why this result is very interesting? It is very interesting because, so if I define qt this way, okay, and I will give a name to dqt over dp, I define it as lt. Okay, it's exactly what I have defined here. So under qt, bt tilde follows the n0t, and I see that, okay, so I do the job for fixed t, let's say, I make this one centered for fixed t, okay, and the family of density I obtain here are equal to this one, and I remark that I have something that is very important, that LT is a martingale under P. Why LT is a martingale under P? But to prove this, okay, take this form here. And you have something here of the form what? Exponential theta bt minus theta square t over 2 with theta that is equal to minus m here. And we have seen at the beginning of the chapter 1 that if I start from a Brownian motion bt, if I transform it this way, then this process, we have done the computation together, this process is a martingale under P. And if I remind, okay, it's probably the last computation we have done, okay, before the holidays, okay, so it was 5 weeks ago, something like this, okay. So I am in this situation, t by t, I succeed to transform bt tilde, okay, into the good Gaussian, that is n0t, but I do it t by t. I have a change of probability for any time t. And then I remark that the stochastic process defined by the related densities, okay, is a martingale under P, okay? And now the idea will be to use both results in order to prove the Girsanov theorem. In fact, after, okay, all the ideas are here, okay, and now I'm going to do the proof. So first, you see that, so let me duplicate this one. So I erase this part. What we are going to do is the following. Here, I have a family of densities, okay, that I can use for any fixed t, okay? And this family is a martingale. We know that a martingale, in fact, is characterized by its final value because, okay, I know that LT is equal to the conditional expectation under P of L capital T given Ft. So if you want to characterize all of them, okay, if you are a martingale, it is sufficient to know what is exactly L capital T. So the change of probability we are going to define is the following. I define a probability Q, and here Q won't depend on the time, and I define it this way. dq over dp is equal to L capital T, okay? It's the change of probability that we are going to use in order to prove that there exists Q making bt tilde a Brownian motion under Q. Okay, so my objective is to prove that bt tilde is a Brownian motion under Q. Okay, so to prove this, I have several possibilities because, okay, we have seen at least 3 ways in the chapter 1 in order to prove that something is a Brownian motion. First of all, I have the definition. Okay, trajectories are continuous. Okay, so I start from 0. My trajectory are continuous. BT minus BS follows the N0 T minus S, and I have independent increments. So to prove that BT tilde is a Brownian motion under Q, I can try to prove this. Okay, that I start from 0. My trajectory are continuous, no problem. Okay, and that BT tilde minus BS follows N0 T minus S under Q, and that BT tilde minus BS is independent, okay, under Q to what happened before. It's something that I can do, but that won't be the best way to do. I have another characterization of the Brownian motion. We have seen together that the Brownian motion is the unique Gaussian process, okay, that is continuous and such that the mean function is equal to 0 and the variance covariance function is equal to the minimum between the instants. Okay, so it's another way to characterize the Brownian motion. It's not the one that we are going to use here. The one we are going to use here is this one. So it is in the chapter 1. So I will just give you the precise this. Okay, it was the proposition 1.3.2 that tell me the following. BT tilde is a Brownian motion under Q if and only if BT tilde is a square integrable martingale under Q such that for all theta belongings to R, the process exponential theta B tilde minus theta square T over 2, this process is a martingale under Q. Okay, so we use proposition 1.3.2, that is an equivalent characterization of the Brownian motion. And if I want to prove that BT tilde is a Brownian motion under Q, it is equivalent, in fact, to prove that BT tilde is a square integrable martingale, okay, under Q, well, integrable and continuous martingale under Q, such that for all theta belongings to R, this process is a martingale under Q. And we have done the proof together of this proposition 1.3.2. And I know that if I am able to do this job in green here, I will have what I want, that is to prove that I am able to find the probability Q that I know explicitly from this definition here, dq over dp equal to L capital T, where L capital T is given by the value of LT, that is this one at capital T, okay? So I have this one, okay? So when I see what I have to prove that BT tilde is a square integrable and continuous martingale. So I have to prove that something is a martingale under Q. And I have also to prove that this something is a martingale under Q. So the first thing we are going to prove here is to make the relation between what is a martingale under Q and what is a martingale under P. Okay, so I change my probability from P to Q. I have martingales that are martingales under P. I have martingales that are martingales under Q. Is there a link between both? The answer is yes, and the answer is given by the lemma written on the slide here. That is the lemma 3.1.1 that tell you the following. A stochastic process MT is a martingale under Q if and only if it is so if and only if, the process LT time MT is a martingale under P, where keep in mind that my small LT here, my LT is given by what I have computed previously. Okay, LT is given by exponential minus M BT minus M square T over 2. Okay, so it means that if I prove my lemma, so if I prove the lemma, it's exactly what we are going to do just after. If I prove the lemma 3.1.1, okay, in order to do this, okay, what I have to prove? I have to prove that BT tilde is a square integrable and continuous. So here, square integrable and continuous, no problem, in fact. No problem concerning the square integrability and the continuity, because keep in mind that my BT tilde is defined as BT plus MT. So my continuity is okay because the Brownian motion B is continuous, and continuity, it's not something that depends on the probability I deal with, okay? And why I am square integrable under Q? Because, okay, I know that, in fact, BT tilde, in fact, follows this one under Q. So of course it is square integrable. So the two main points I have to prove, okay, is that BT tilde is a martingale under Q, and that this process is a martingale under Q. I have a characterization of the martingale under Q here. So it means that in order to prove this, okay, it remains to prove, in fact, 2 points. That is, so to prove that BT tilde is a martingale under Q, I have to prove that LT BT tilde is a martingale under P, in order to prove this first point using the lemma 3.1.1. And the second point is to prove that LT exponential theta BT tilde minus theta square T over 2, this one is also a martingale under P for all theta belonging to R. If I prove these 2 points, from the lemma 311, I have the 2 points underlined in red here, and so I will have from the proposition 1.3.2 that BT tilde is a Brownian motion under Q. So I have to do 2 things, in fact. First, I have to prove the lemma 311, and then I have to prove, okay, the fact that LT BT tilde is a martingale under P, and that LT time this exponential is a martingale under P, where LT is given by this expression. Okay? And why this lemma 311 is interesting for me? It's because, okay, so here a priori I have to prove these 2 statements under Q, but my initial hypothesis was that BT is a Brownian motion under P. So I know a lot of properties of B under P, and that's why it's a priori more comfortable for me at this stage to work under P. And so, okay, I transform my problem under Q into a problem under P. Okay? So I have this one. So let's duplicate this slide here. And we are going to do so the proof of the lemma 311. So I just keep this in mind. Okay, I write it here, that you have dq over dp that is equal to L capital T, L small t being a martingale under P, I have this relation where L small t is given by this one. So you have everything. So proof of lemma 3, 1, 1. Okay. So a little remark first. So we know that if capital X belongs to L1 of omega A Q, by definition, the expectation under Q. So here I will make difference between E, capital E, that is the expectation under P, and EQ, that is the expectation under the new probability Q. So I know that this one, by definition, is given by the expectation under P, in fact, implicitly, of L capital T X. It's because I have this. I have the definition of the density of Q with respect to P. Okay, so the expectation under Q may be written as an expectation under P multiplying by the density of Q with respect to P. Okay, nothing new. Let's see what happened here. I said the following. Suppose that if X is in L1 of omega FTB of Q. So here it just means that X is FTB measurable. So it is in L1, it is in this space, but I impose it to be FTB measurable. Okay. So if X is in L1 of this one, okay, I say the following. What is the expectation under Q of X here? Of course, this set is included in this one, so I can use this formula here. So it is the expectation of L capital T times X. But I know, so here my T is between 0 and capital T. I know that the expectation is equal to the expectation of the conditional expectation given F small t. So I can write this. And I know that X is FTB measurable. So I can remove it from the conditional expectation, and it remains the conditional expectation of L capital T given FTB. But I know what is this term. Because L small t is a martingale under P, I know that this one is simply equal to LT. And so at the end, if X is FTB measurable, this is simply equal to the expectation of L small t capital X. Okay? So what is the meaning of this one? It means that if you have no hypothesis concerning the measurability of X with respect to my filtration, to pass from the expectation under Q to the expectation under P, I just multiply by L capital T. If I have a little bit more knowledge concerning the measurability of capital X, that is capital X is FTB measurable, then in fact, this formula is true, but I can improve it a little, saying that the expectation under Q of X is equal to the expectation of X multiplied not by L capital T. This is true if I multiply by L capital T, but if I multiply by L small t. And the L small t that will appear here will be the one, okay, that will enter in the proof of my lemma 3.1. So this was a remark, let's say here. It was a remark. And now we are going to prove this lemma 311 using my remark here. So I want to prove that MT is a martingale under Q if and only if, okay, this process LT times NT is a martingale under Q. So we are going to consider, okay, the following. So let Z, okay, or let Y being FSB measurable and bounded. And we are going to consider the expectation under Q of MTY. And why I do this? Because I want to be able to compute the conditional expectation under Q of MT given FSB. So I come back to the definition of the conditional expectation. I consider Y that is FSB measurable and bounded. And I consider this one and I try to put it on the form of, okay, the expectation under Q of something that is FSB measurable multiplied by Y, and this something that would be FSB measurable will be the conditional expectation of MT given FSB under Q. Okay, so I have this one. So, and I consider here that my T is strictly greater than S, as usual. What is the measurability of what I have inside here? The measurability of what I have inside is to be FT measurable for this one and to be FS measurable from this one. So the product here, this one, is necessarily FT measurable. And since I have something that is MT measurable, I can use my previous remark. That is the expectation under Q of something that is FT measurable can be written this way. So I will transform my expectation under Q into an expectation under P, that is this one. Expectation under P of MTY multiplied by LT. Okay? And here I have something that is FS measurable here and something FT measurable and something that is FS measurable here. By definition of the conditional expectation under P, this term is equal to the expectation under P of what? Of the conditional expectation under P of LT MT given FSB multiplied by Y. Why I have this is just the definition of conditional expectation. Okay, the conditional expectation is the random variable that fulfills this relation for any Y, FS measurable and bounded. So I have this. Okay, and what can I do with this? At this stage, I can do nothing. I just use the definition of the conditional expectation. Okay. So my aim at the beginning was to compute a conditional expectation under Q. I used my previous result in order to write it as a conditional expectation under P. Okay. And I use the definition of the conditional expectation under P. And now my aim is to come back to an expectation under Q. So I start from an expectation under Q. I want to finish with an expectation under Q. And so I just remark that here I have something that is FSB measurable. So I can use this result here. This result that tell me how to pass from something that is okay under P to something that is under Q when I have inside something that is FT or here FSB measurable. And I say that here, this one is what? I can write it as the expectation under Q. Okay, so using in fact star, that is this term for t equal to s. Expectation under Q of what? Of 1 over Ls, expectation under P of LT MT given FSB Y. So I have this one. So I use here this relation for Ft. I use the definition of the conditional expectation under P of the process LT time MT, and then I come back to Q using once again this one for T equal to S. What I have at the end, I have proved that this one is equal to this one. So let's write it. I have proved that the expectation under Q of MTY is equal to the expectation under Q of 1 over Ls expectation under P of LT MT given FSB Y. By definition of the conditional expectation, since here I have something that is FSB measurable, by definition of the conditional expectation, I can say that the conditional expectation under Q of MT given Fs is equal to what? But exactly to this term here, by definition of the conditional expectation. The conditional expectation of MT given Fs is equal to this term here, because here this term is FSB measurable and fulfills the definition here that is true for any Y, okay, Fs measurable and bounded, and I have this relation. And in fact, my lemma will be finished because this one is equal to Ms, that is MT is a martingale under Q, so this one is equal to Ms if and only if, but this one is equal to Ls Ms. So this term is equal to Ms if and only if this one is equal to Ls multiplied by Ms, because I divide by Ls here, okay? So in other words, it's exactly what I want to prove. That is, this conditional expectation is equal to this one, that is M is a martingale under Q, if and only if this equality is true. And what is this equality? This process, LT times MT, is a martingale under P. So I am able to characterize a martingale under Q into a martingale under P. MT is a martingale under Q if and only if LT times MT is a martingale under P. Okay, so I have done the proof of the lemma 311. And what is nice with this lemma is that we are going to use it, because keep in mind what I want to do. I want to prove that Bt tilde is a Brownian motion. And we have seen together that from now on, since we have the proof of the lemma 311, it will be sufficient to prove that LT times Bt tilde is a martingale under P, and that LT multiplied by this term here is also a martingale under P. Okay, so it's what remains to prove in order to prove this result. So it's what we call the Girsanov theorem. Okay, it's a basic version. I will do some comment after on some extension. So basic version of the Girsanov theorem. So by basic version, it will be already, okay, the one needed in Black-Scholes. Okay. That tell me that if M is an arbitrary real number, under Q define this way with L capital T that is completely explicit and given by exponential minus M B capital T minus M square T over 2. So under the probability Q defined this way, B tilde is a standard Brownian motion. It's how to change the probability in order to make B tilde a new Brownian motion under this new probability. And if you have understood what I have said, I repeat that what I have to do the proof of this proposition, I have simply to prove that LT BT tilde is a martingale under P. I have to prove that LT times this process, this exponential is a martingale under P because, okay, if I prove this by the proposition 1.3.2, I prove that I am a Brownian motion. It is the characterization of the Brownian motion proved by in proposition 1.3.2. So I have two things to deal with, okay, this one and this one. So we are going to start with this one because this one is very simple, okay, and this one is not complicated, but the computation are a little bit longer. Okay, so let's do the proof of this. I have two things to prove. The first, so we are in the proof of proposition 3.1.1. Okay, I have two things to prove. The first thing is to be interested in LT exponential theta BT tilde minus theta square T over 2. And I want to prove that you have here a martingale and the P. Okay, so let's do the job. So what is LT? So first I know what is this expression here. So this is equal to exponential minus M BT minus M squared T over 2 multiplied by this exponential, that is exponential theta. So BT tilde is equal to BT plus MT minus theta square T over 2. And I see that I can express it the following way. I can express it as exponential theta minus M BT. So it's this term here, BT, BT, so to obtain this one. And then I have this one, and this one, and I see that in fact, this one, and this one may be expressed as minus, so I have T over 2 that I can put into factor, okay? And if I do this, okay, I have what? Theta minus M square. So in order to prove that this is a martingale under P, in fact, I have to prove that this one is a martingale under P. But how I can write this one? I can simply write this one as exponential theta tilde BT minus theta tilde square T over 2. And I know, so where theta tilde is equal to theta minus M. And we know from, oh, I can give you maybe the precise thing, okay, I know from the beginning of the chapter 1 that here you have a martingale under P. Because I know that BT is a Brownian motion under P, and we have proved together that if I transform a Brownian motion this way, I obtain a martingale under P. Okay, so I have done half of the job. I have proved for the moment that this one is a martingale under P. If I prove that this one is a martingale under P, then I will know that BT tilde is a Brownian motion under Q. So let's do the job for this one. So I erase this because I have done the job. And the second point I have to do, is to prove that, okay, LT BT tilde, the martingale under P. And here I have to do a few computations. Okay, so let's do the job. So I am interested in the conditional expectation under P of LT BT tilde. So something that I can write as, okay, so BT tilde is just BT plus MT that I multiply by L small t, that is exponential minus M BT minus M square T over 2. And I have to compute the conditional expectation given FSB. And I have to do this for T strictly greater than S. Okay? So first of all, okay, what can I do? I can put exponential minus M square T over 2 into factor. This one that I can remove because it's the constant. And then I have two terms, that is the conditional expectation under P of BT exponential minus M BT given FSB, okay? And then I have the term just expectation under P of MT exponential minus MBT. Okay, so I can write it this way. It's MT exponential under P exponential minus M BT. Given FSB. I close my big parenthesis. Okay, so there is one, so, and don't forget that I have this one before, okay? So in fact, there is one term that is easy to compute, that is this one here. This one with this one before. In fact, it wasn't that clever to remove this one because for one of the two, okay, if I put it inside, it's better to compute because, okay, what I know, I can write it here. I know that from what I have already said previously, if I compute the conditional expectation under P of exponential minus M BT minus M square T over 2 given FSB. But I know what is this because it's a transform of the Brownian motion. It is of the form of exponential theta BT minus theta square T over 2 with theta that is equal to minus M, okay? And so I obtain here, I know that this term is a martingale under P, so this term is necessarily equal to exponential minus M BS minus M square S over 2. It's from the beginning of the chapter 1 when I know that this transform of the Brownian motion is a martingale under P, so I have this. So it implies that my term can be written this way. So I will have this one multiplied by this one, that is exponential minus M square T over 2 multiplied by this that I will have to compute. plus by the term I have computed in blue here, that is what? Don't forget the mt before, m times t time this one, exponential minus m bs minus m square s over 2. Okay, so I have this, and it remains to compute this term here. It remains to compute this term. So what is this term? Here I have this conditional expectation to compute. In order to compute this conditional expectation, we are going to do as usual, that is to make appear the increments in order to have a part that is independent and a part that is FSB measurable. So I can write the things this way here. BT minus BS plus BS, and I have exponential minus M BT minus BS plus BS given FSB. Okay? So what I will underline in green is something that is FSB measurable. What I will underline in blue is something that is independent of FSB. And I know from a proposition that I have computed, that I have done in the chapter 1, that this conditional expectation here is necessarily a function of the measurable part, where phi of x is given by the expectation of BT minus BS plus x exponential minus m BT minus BS plus x. Okay, and it remains to compute. It remains to compute this expectation. So let's do. So I do the job here. So I have this one, I have this one, I have this one. Okay, so I do this. I erase this part here, all the things I have done. I will come back on this point later. And here I am just interested in this computation. Okay? In this computation. I remark that under P, BT minus BS plus X, I know what is the distribution of this one. So under P, this one follows the N, X, T minus S. So if I consider capital X a random variable having this distribution, what I am interested in here is just in the computation of the expectation of X exponential minus X, simply. Okay, so it's what I want to do here. Exactly what I want to do. Okay, so I have to compute this term for X being nx t minus s. But let me remind the following. I know the moment generating function of a Gaussian. So if you have X that follows the n m sigma square, we know that the expectation of exponential, okay, t x is given by exponential t m, okay, plus what? Plus sigma square t square over 2. Okay, So it's the moment generating function of n m sigma square. Okay. What I want is this one here. I want to make the x appear here because here I have my exponential. Okay, so if I don't have this term, if I erase this one, I am able to compute, but I have the capital X. But in order to have the capital X here, I can compute the derivative. If I compute the derivative of this term, I obtain what? I obtain that the expectation of x exponential tx, I compute the derivative with respect to t, is equal to this exponential, and the derivative of this exponential is u prime exponential u, and u prime being equal to what? I have here m plus the derivative of this one with respect to t, that is sigma square t exponential t m plus sigma square t square over 2. M plus sigma square t exponential tm plus sigma square t square over 2. And so I am able to compute this term, okay, plugging inside. So it's for m equal to x, sigma square equal to t minus s, and small t here equal to minus m. Okay, so let's do the computation using what I have done here. So it's m being x. So it's x plus sigma square being t minus s. Okay. So this one, so x plus t minus s, okay. Time t, what is t here? My t is minus m. So I have here a minus multiplied by m here. I close my parenthesis. Excuse me 1 second. Okay, so this exponential of t that is equal to minus m, the mean that is x, plus sigma square that is t minus s, t square that is just equal to m square over 2. Okay, so I have this one. I obtain for phi of x minus t minus s m exponential minus m x plus t minus s over 2 m squared. If I come back to my slide here, my objective, okay, was to compute the conditional expectation of this term here. And we have seen together that the conditional expectation of this term is equal to what? Is equal to this quantity here. So it is, okay? So we are going to change a little the things, okay? So I use this one. I erase this intermediate step here. And what I have obtained, I obtain for this one here, exponential minus m square t over 2 phi of bs, plus mt exponential minus mbs minus m square s over 2. That is this term here. So now I can erase everything here because, okay, I have just copied this part, okay, where my phi was computed at the previous step. And what is my phi of x here? So let's come back to what I have done previously. Phi of x is this one, so that I have to write for x equal to bs. So it will be bs minus t minus sm. So I copy, okay. I obtain exponential minus m square t over 2 factor of phi of bs, that is bs minus t minus sm, bs minus t minus sm, okay, and exponential minus bs exponential minus m bs plus t minus s m square over 2 plus t minus s m square over 2. So this is this first part here. Here it's this one. And I don't have to forget this one. That is plus mt exponential minus m bs minus m square s over 2. So, and I hope that I will have some simplification, and I have some simplification, because here you have mt time exponential minus mbs minus m square s over 2. It's exactly what I obtained. So this one can be simplified with this one, because with this one I have minus t, okay, minus mt is the same exponential here. No, I have to be a little bit more. Yes, excuse me. So yes, exactly. I have this simplification because I have minus tm time this exponential, okay, and time, I don't have to forget this one. So I have here, if I multiply, okay, this term here make the t disappear here, in fact, okay? So I can simplify this one with the t here because it's an exponential. So it remains this one, and at the end, if I continue my computation, I have what? I have bs plus minus minus plus ms exponential minus m bs minus s m square over 2. And what I have proved that this one, the conditional expectation of this one given fsb is what? It is exactly the value of this one at the point s, bt plus mt bs plus ms exponential minus mbt minus m squared t over 2 exponential minus mbs minus s m square over 2. So I have proved that this one is a martingale under p. So I have proved that this one is a martingale under p. And if you come back to what I want to do, it was this one. I have proved in the previous step that this was a martingale under P. I have proved now that LT BT tilde is a martingale under P. For the lemma 311 and the proposition 1.3.2, I have that BT tilde is a Brownian motion under Q. So I have proved, okay, what we call the Girsanov theorem in its basic version, okay? That is, if I have bt tilde defined as bt plus m time t, where m is a real number, if I define q this way, I obtain that under q, bt tilde is a standard Brownian motion. Okay? So you see already that, okay, this proof is not that complicated, but it needs some computations, okay? And we are going to have a look now, okay, on the real version of the Girsanov theorem, okay, that is a little bit more complicated to prove, in fact, and more complicated to prove. But I will do just some comments concerning this general version. So I have done the proof of the basic version, but what is nice is that the basic version is what I will need in chapter 5. So in some sense, okay, I have proved, okay, the version I will need in my chapter 5 of interest. Okay. So I have this. Let's discuss this and this. Okay. Here you have the real version of the Girsanov theorem. So I will explain a little, okay, the things and make some link with what I have done before. So previously, I was interested with bt tilde that is equal to bt plus m time t, okay? And I have proved that, okay, if I define dq over dp as exponential minus, so what is what? Minus M B capital T. Okay, so it was this one, minus M B capital T. Okay, it's this one, minus M square capital T over 2. And I have defined LT that was, okay, exponential minus M BT minus M square T over 2. And I know that this was LT is a martingale under P from the property of the transform of the Brownian motion. Okay. So I have this. Okay. Now we are going to be in a generalization of this result. So we are going to transform the Brownian motion into a shifted one. So the BT tilde I consider in the general version of the Girsanov theorem is BT plus, so here my drift, okay, was my translation, if you want, was M times T, something that was very simple. Okay, I can make it more complicated. 0 integral between 0 and T of theta of S ds, where theta belongs to H2 log. I want to make this Riemann integral well defined, and keep in mind that, okay, I can define it for theta belonging to H2 log, okay, the set of the stochastic processes that are progressively measurable and such that the integral of the square is finite, okay? Okay, so this one means just that I am progressively measurable and that the integral of the square is finite, P almost sure. So, of course, I can obtain this one from this one. If I take here theta of S that is equal to a constant, in fact, I recover my previous version. So this sense that I say that the version I have proved is a basic version, because it will be just, okay, a particular case of the real version in the case where my theta can be a progressively measurable stochastic process in H2 log that is not necessarily constant. Okay? So what is the real version of the Girsanov theorem? It tells you the following. So it tells you that BT tilde defined this way is a standard Brownian motion under Q, where Q is defined this way, if the process LT defined this way here is a martingale under P. Okay? So if this is a martingale under P, then BT tilde is a Brownian motion under Q fulfilling this condition. Okay? So here, if I take in this statement, if I take theta here in red, I will put theta constant. If theta is a constant here, what I obtain for this one, but I obtain for LT, it is just exponential minus, so if theta is M, it's minus M BT, and here minus 1/2 M square T, so it is minus M square T over 2. So if theta is equal to M, the LT I obtain here is this one, exactly this one. Okay, exactly this one. And the dq over dp I obtain here is exactly this one. But what is nice in my basic version is that here in the Girsanov, the true Girsanov theorem, you have an hypothesis to check. That is, you have to prove that this one is a martingale under P. Okay? In my basic version, it's not something that I have to prove because my LT is given by this one. And I know from the result of the chapter 1 that in the basic case where theta is a constant, LT is necessarily a martingale under P. Okay, so it's not something that I have to check because it is true from the chapter 1. But if I want to have this result in grid generality, I need to check that this process that is just an extension of this one is a martingale under P. And if it is true, then I have this more complex perturbation of the Brownian motion that will be a Brownian motion under Q. Okay? So it means that in its general version, if I want to use the Girsanov theorem, I have to check that this process here is a martingale under P. Okay, so the process of interest is the extension of this one that is LT equal to exponential minus integral between 0 and t theta of s dbs minus 1/2 integral between 0 and t theta s squared ds. I see that this process is not that complicated a priori. It is just the exponential of something that has this Ito decomposition here. So let's define xt that is equal to minus the integral between 0 and t theta of s dbs minus 1/2 the integral between 0 and t theta s squared ds. So I have this decomposition. So if I write the decomposition here in the differential form, I have d of xt, that is what? Minus theta t dbt minus 1/2 theta t squared dt. And I see that my LT here is just exponential of xt. So it is easy to obtain d of LT from the Ito formula applied to the exponential, because here I am exactly under the hypothesis. My theta here is in H2 lock. H2 lock. And this one, this is the square of someone that is in H2 lock. It's something that is in H1 lock. Exactly. Okay, the condition I have imposed, okay, on an underlying process X in order to be able to apply the Ito formula to, okay, a mapping that is here the exponential. So from the Ito formula here, I obtain what? I obtain f prime of xt d of xt plus 1/2 f second of xt. And I have what? Okay, I have here the square of the term in front of dbt in the Ito decomposition of x. So that is here theta t squared dt. If I handle this, so I have obtained d of LT that is equal to f prime of xt d of xt plus 1/2 f second xt theta t squared dt. Keep in mind that f of x is equal to the exponential. So f prime of x is equal to the exponential. F second of x is also equal to the exponential. Okay, and I have, okay, LT that is the exponential of xt, and d of xt that is given by this one here, that is minus theta t dBt minus theta t squared dt over 2. So I plug inside the little formula to obtain that d of Lt is equal to what? So I have here f prime of xt, that is simply Lt. D of xt I plug minus theta t dBt minus theta t squared dt over 2 plus 1/2 f second of xt, that is just Lt because f second is the exponential, theta t squared dt. And I see that I have a simplification here. This one simplify with this one, and at the end, I obtain that d of Lt is equal to minus theta t Lt dBt. So you have the Ito decomposition of Lt. Okay? If I come back to my Girsanov theorem, okay, I am interested in proving, if I want to check the hypothesis, that is Lt is a martingale under P, okay? I have to check this one in order to apply to my results. And I know that Lt is given by this one. In the course, okay, so it means that Lt is up to a constant, okay, something that is simply, so this one tell me that Lt is equal to L0 being equal to 1, okay, plus the integral between 0 and t of minus theta of s Ls dBs. So you have Lt that is up to a constant, that is up to its initial value, a stochastic integral, okay? In the Girsanov theorem, I have to check that this stochastic integral is a martingale. So I have condition on this in order to obtain a martingale. And typically, okay, I need that this process here, that this process belongs, for example, to L2 prog. If I am sure that this one belongs to L2 prog, I am sure that this one will be a martingale, okay? But you see that here, you have L inside there, here and inside in the integrals, okay? So it's a condition that depends on the process itself, okay? So a priori, it's not something that is easy to prove. So it may be complicated to prove that this one is a martingale under P. In the case where theta is a constant, I recover this result from my result in the chapter 0, okay? If theta is a function of S, no problem also, okay? So maybe I can try to, after I will check, okay, just after. But in fact, to conclude this part concerning the Girsanov theorem, just let me give you up to now the most general condition that is known in order to ensure that this hypothesis is fulfilled. That is a condition on theta in order to make Lt a martingale under P, and so in order to be able to use the Girsanov theorem. This condition is just what we call the Novikov condition that tell you that the process Lt is a martingale under P if I have this expectation. So it's the expectation of the exponential of 1/2 integral between 0 and t of theta s squared ds. So it's a strong integrability hypothesis for this one that will ensure for sure that Lt in this case is a martingale under P, so that I am able to apply the result concerning the Girsanov theorem. Okay? So just a remark concerning this, because I want to show you that you have other situations where it is easy to check, okay, that Lt is a martingale under P. So it's an example. So what I have done the job for theta equal to a constant. We are going to do the job for theta equal to a mapping. So here I consider Bt plus the integral between 0 and t of h of s ds. where H is not something in H2 log, something that is more restrictive, that is just to be in L2 of 0 capital T. And the case where my process theta is not random, it's a deterministic mapping that is square integrable. Okay? So I have this. So you have here, okay? So if I come back to the previous statement, okay, I have this, and I have to check that this is a martingale under P. In my particular situation here, LT is equal to what? It is exponential of minus the integral between 0 and T of H of S dBs minus 1/2 the integral between 0 and T of HS squared ds. Okay? And I say that in this case, LT is a martingale under P. Why I have this? If I compute the conditional expectation of LT given FSB for T strictly greater than S, so what I have, in fact, we are going to make appear as usual a part that is measurable and a part that is independent, and I can write it this way. I can write it as exponential minus what? So the integral between 0 and T that I will decompose in an integral between 0 and S, okay, of H of U dBu plus the integral between S and T, H of U dBu, okay, minus 1/2 and so on, okay, given FSB. So I just copy this, I plug it inside, and I separate this integral between 0 and T in a part that is Fs measurable and a part known to be, okay, so I have here in blue something that is FSB measurable. You have here a part that is independent with respect to FSB. And from a well-known proposition from the course, okay, what is this? This is a function of the measurable part. Where phi of x is just now an expectation. It's the expectation of what? Exponential minus x plus integral between S and T H of U dPu minus 1/2 the integral between 0 and T H square of S ds. But in this very particular situation, it is very easy to compute this term here. It's very easy to compute this term because here, I want to do the computation. You will finish, so finish at home here to trade. Why it's easy to compute? Because here you have a Wiener integral. So this one, you know the distribution of this one, it follows a Gaussian with mean x and variance here. So this one is a constant that you can remove from the expectation, and here you will have to compute something that is just in relation once again with the moment generating function of a Gaussian that you are going to be able to compute explicitly. Okay, so in the case where my drift take this form, the integral of a mapping, not of a stochastic process, I can always apply the Girsanov theorem. It's not necessary to use this condition that is fulfilled in my particular situation, but I can do it explicitly without supposing that this proposition is true here, okay? But if you come back to my case, what is difficult in general in order to check this condition is that here you have in general, when theta belongs to H2 log, you have something that is no more Gaussian. So to prove that it is a martingale under P, you don't have to use computational arguments, but arguments that are theoretical arguments that are out of the scope, okay, out of the scope discourse, in fact, okay? Because I need the notion of local martingale, okay, and so on, but it's not something that I have dealt with in this course, okay? But just keep in mind that I have a very general version of the Girsanov theorem, the one explained in this slide here. I have proved it for theta equal to a constant, okay, explicitly. That will be the version I will use in the chapter 5. I have commented the theorem saying that be careful, I have an hypothesis to check. The hypothesis to check is that LT is a martingale under P. In my basic version, LT is necessarily a martingale under P because it's a result from the chapter 1. For more general framework, I have to work. In the case where theta is a mapping and not a stochastic process, in fact, it's okay because I deal with Wiener integral, okay, that are Gaussian. So I am able to compute explicitly the conditional expectation of LT given Fs and to prove that it is a martingale in these conditions. But when theta is more complex than a mapping, that is a process in H2 log, but it's a real, okay, thing to prove that LT is a martingale. And to conclude this part of the chapter, I just say that there exists a result called the Novikov theorem that is a criteria easy to check on theta in order to prove that LT is a martingale under P, and so in order to be able to apply the Girsanov theorem. Okay, so I will do a little break now, okay, and I will end this chapter, okay, in another video in order, okay, to cut the chapter in two parts, the part concerning Girsanov and the part concerning the martingale representation theorem that I will do in the next video. So see you in a few minutes.